With my warm greetings, I extend my warmest welcome to each and everyone invited here. I am Sushmita, doing my second year in the Department of Electronics and Communication Engineering at Chennai Institute of Technology. We are analog beings living in a digital world facing a quantum future. CIT, the college has not left any stones unturned in making its students worthy citizens. The time as a caterpillar has expired and the wings are ready. Yes, it is about transforming lives. It's been just 10 years since CIT has stepped in, but the victories of CIT are huge. It is indeed a privilege for all of us to get the opportunity of attending this webinar. To be short and crisp, yes, it is about Knowledge 4.0. Today we have our expert Mr. Murugan Balabaskaran and our organizing secretary Dr. R. Dhanagopal. I feel much pleasure in welcoming you all. So talking about our expert's profile, he has completed his BE Electronics and Communication Engineering in University of Madras. Followed by that, he has completed his MTech in the domain of VLSI systems in National Institute of Technology, Trichy. He has filed a patent in apparatus system and method for indicating status of multi-link network ports. He has got many awards and honors like Popular Choice Award for Paper in Innovation Bazaar in 2018. Talking about his working experience, he is now a technical manager in Western Digital and he was a technical manager in Intel Corporation and before that a member technical staff in Juniper Networks. He has experience in networking platforms, mobile platforms and consumer product platforms. I feel much pleasure in welcoming you, sir. Thanks for giving me the opportunity. Thank you.
Thanks, Sushmita. Thanks for the nice introduction, and I'm very much impressed on the CIT and the member staffs, and thank you very much for the opportunity to explain about the ASIC domain and whatever the things I'm going to experience in my life with respect to the semiconductor industry. I like to share with you guys, and if any doubts or anything, if you have, you can stop me and you can ask the questions. So you can also type the questions on the message comments actually. So based on that, we can discuss also. So going forward, shall I start the discussion?
You can share your slides.
So basically, I'm going to discuss about the ASIC design flow and the importance of the pre-silicon validation. And the agenda for this discussion is I'm going to go through the basics of ASICs and.
Excuse me, sir. Sorry, sir. Try not share, sir. Can you share your slides?
I'm sorry. Yeah.
Start.
Yeah.
Please share.
Sure. I'm sorry about it. So you guys able to see my screen?
Yes, sir. Yes, sir.
Sure.
Make it full screen, sir. Make it full screen, sir.
Yeah.
Yeah, fine, sir. Good, sir. You continue, sir.
Thanks.
Thank you.
So basically, I'm going through the design ASIC design flow and the importance of pre-silicon validation. And so the agenda for this today's meeting is ASIC versus FPGA. So I'm going through what is ASIC and what is FPGA, the basic differences. And after that, I will go through the ASIC design flow and the complete design flow of ASIC. And each flow, there will be different stages of before going to the chip. Actually, there are the different stages. I will go through the basic stages and I will cover it basically what is that stage and what we will do in industry. And after that, I will go for what is pre-silicon validation, why we need pre-silicon validation, and what are the different types of pre-silicon validation environment. And I also going to cover about what is emulator and examples of ASIC on emulation and FPGA platforms. And I also going to cover about pros and cons of different pre-silicon validation platforms. Let me see, and I will try to cover it within this time stipulated time period. Yeah. As you are already aware, and in your college course also, you might be heard about what is maybe the word FPGA and ASIC. You guys heard about it? Anyone Any one of the students, please?
Sir, they're not able to join with us. Sir. At the
Sure,
end of
sure.
the session, we will take the questions.
Definitely, sir. Sure, definitely. I will go through the differences. So I thought it will be an interactive session. So definitely, due to the pandemic situation, I had to understand. Definitely, I'll go through the differences, basic differences. Then later on, we'll have a QA sessions. Sure. So basically, FPGA is a reconfigurable chip actually. So basically, FPGA is a field programmable gate array. That's what the conventional description we say. But the FPGA is built up with SRAMs, and we can do reconfigure the complete circuit of FPGA, and you can make it as a whatever design you want to port. We can do it based on the FPGA design we want to have. But ASIC is a permanent circuit, and it is very specific to the application what you are planning to do actually. And to make an FPGA configurable, and you want to have some particular application you are targeting, you can use hardware description languages such as Verilog and VHDL. And nowadays we started using System Verilog. And for ASIC, same thing. We will use the same hardware description language and System Verilog, and VHDL. And if you want to do any FPGA-based project or anything you want to start, it is very cheap. And that's why the industry, if you are having a small level of volumes, then the industry will prefer to go with FPGA-based design. And the cost will be started with the USD of $30. But the ASIC manufacturing will be a biggest challenge, and it will be cost millions of dollars. So when we go for a design for any FPGA-based design or ASIC-based design, and we won't directly target, we will start with the FPGA-based design, we'll go for a ASIC. So it depends on how much volume you are planning to do that actually. If you want to do a design and means a specific application-oriented design, and it will be very less number of production, then you can go for FPGA-based design. And if you want a mass production, you want to have a multiple chips, and you want to targeted very high number of volumes, then you can go for ASIC production, because the cost will be lesser based if you go for a high mass production in ASIC. But the FPGA will be mass production, the cost will be very high. And FPGA is targeted, it's a prefixed design, and the energy will be less, but the power efficiencies are more actually. The powers are more, but in ASIC the power is more actually. Power consumption will be less actually compared to FPGA. Power consumption in ASIC is less basically, because you are targeting low power, you are targeting much more efficient power actually in ASIC. But in FPGA, it's a predefined configuration chip, and based on the nanometer technology, whatever the FPGA manufacturer providing, that is the only technology you can work on it. And that currently it is 28 nanometer, now it is 10 nanometer technology based on the FPGA. So Xilinx UltraScale came, and those are all the designs with the 10 nanometer technology FPGAs came actually. But now it is equivalent to ASIC, but it won't be as efficient as ASIC design. And operating frequency also is fixed with respect to the FPGA configuration, because if you go for any design in FPGA, and there is a limitation that you cannot work more than the particular operating frequency prescribed in the datasheet of an FPGA. For example, if I took a Xilinx-based design or Ultra-based design, so Xilinx means you can take a Vertex 7 series or Vertex UltraScale series. There will be a fixed datasheet will be provided for the FPGA, and in that FPGA they will specify this is the time frequency can be adopted for your design. But for ASIC, it is not like that. Your fabrication process will vary. So which node, which technology library. So now Intel kind of companies are targeted for 5 nanometer technology. So now the power consumption has been reduced, and frequency bandwidth also got increased with respect to the ASIC manufacturing unit, and we can achieve in terms of gigahertz. But in ASIC, in FPGA, gigahertz frequency targeted will be lesser. So it will be in terms of 700 to maximum 800 megahertz as the reference clock to the FPGA based designs. And one more drawback with respect to FPGAs, you cannot port any analog designs like SERDES or any radio things, can ADC, analog to digital. So those things cannot be targeted in the inside FPGA, but across the FPGA board, you are manufacturing a prototype kind of thing, then you can keep FPGA, and next to the FPGA you can keep all the necessary SERDES and all these things, analog blocks. You cannot put any analog portion inside FPGA. But ASIC is not like that. It is a mixed kind of signals can be done, and you can have all kind of chips. So that's how the mobile chipset will comes actually. So if you take a mobile chipset, you have a Wi-Fi, you have a processor in it, and you have all the analog portions also interacting with it actually. But in FPGA side, you have externally you can keep it actually, but internally you cannot keep anything inside the FPGA analog portions. So FPGAs are highly suited for different applications, radar, cell phone base stations, and you can also port a better algorithm. And not only that, nowadays the share markets, you can see share markets have been using FPGAs actually, because the time intensive algorithms like which share and which price, it is time matters basically in the share markets. What they will do, they will put their algorithm and they make it work it in FPGA, because compared to software, if they put it in hardware, the speed will be more actually, because you defined everything in hardware. Then the fast and the application runs very faster. So that's why they are going for this kind of time intensive logics, everything they are going for FPGA based thing, and they can improve their algorithm. So those things are now came into picture recently. And ASIC is suited for the specific application, and as I told earlier, so it is done in a mass production. The ASIC designs are valid, but in FPGA it is not like that actually. Okay, and moreover, okay, so let's talk about next thing is the prototyping. So preferred, so FPGAs are not only used for certain application. In order to make your ASIC design, and you want to make a proper ASIC design, and you want to have a quality tape out, then you can also use FPGAs for that actually. So how they are using, that's what we call it as a prototyping. The word prototyping and validation means that you can mimic, or you want to validate the tape out RTL inside FPGA and make sure your complete RTL works fine on the FPGA platform. So that's what the word called prototyping, FPGA prototyping we call. So this is one of the major advantage of FPGA, and yeah, it is and ASIC it is not possible, because once a chip is done, you can use for that particular application only. You cannot do anything apart from doing what is specific to that particular chip actually. And FPGA engineers generally do not care about care for backend design, because place and route and automated place and route will happen. Synthesis will also happen automatically, because it's predefined layout inside FPGA, and your logic will sit inside the FPGA, and they know what is the clock structure, and everything is defined properly inside that. So it will use those logics, and it will go and sit inside that LUTs, which is nothing but a SRAMs basically. But in ASIC, it is not like that. You have to do all the complete clock tree and physical layout, manufacturing and fabrication, and post-silicon validation. Everything has to be done. Then only your quality ASIC tape-out will happen. So let's get into the ASIC flow. So to make a chip, so you can see 1, 2, 3, 4, 5, 6. So to make a chip actually, to reach this level, there are multiple teams and multiple process steps actually involved. So starting from chip specification, and next up what the chip specification I will come into the later. Starting from the chip specification, means the architecting, what kind of chip actually we want to develop first, and what kind of specific application you want to develop actually, what for this ASIC chip actually you want to develop. And those discussions will go through, and what is the size and what power consumption and what is the area of the size actually. So the packaging team will come into picture, and verification team will be coming to picture, and DFT teams will come into picture, and all the place and route teams will come sit together and we'll discuss about what is the plan, within how many months we can deliver this tape out actually, and what is the size of these are the architecture discussion will be defined, and it will be captured in the form of chip specification. And then only the designers will start doing the RTL coding. So RTL coding in the sense, it can be a system Verilog hardware description language coding, it can be system Verilog, it can be a Verilog, it can be VHDL. Nowadays, all the whole industry is going further on system Verilog. And so these activities, not like a sequential order, will start once the chip specification is defined. Everybody's pre-planned what are the activities I need to do for this chip tape out. So everything parallelly they will plan. So, for example, a designer wants to understand the once a spec is defined, that design team will start developing the designs, and verification team will define how to verify verify those designs, and they will start doing the bus functional model, UVM model, and they will separately their team will start work on the bus functional model. And what they will do all the scenarios, they capture what are the test cases involved to test this design, everything, the specification, test specification sheet they will prepare, and they will start doing the testing actually. So once the design is ready, it will be in terms of phased wise. So for example, a complete chip cannot be done in one single phase. So there will be a stage wise release will be done by the design team, and incremental they will call it as R0, R1, and finally is the final release, means of the design basically. So the stage wise release will be done, and they will based on the features. For example, we have 15 features in their design. They will release stage wise, in the sense each release will have a few features, and based on that they will release it to the verification team. Hey, these are the features I am going to release it to you. You start doing verifying these features. And after that, RTL synthesis team, what they will do, their work is to do synthesis, whether the logic is properly synthesized, and it will what is expected in the behavioral model, and same to be synthesized, and it should fit into the ASIC domain. So it are the constraints they will develop, and they will make it properly. Then at least everything has to done properly. Then they go for a partitioning of chip. So partitioning is again a big process. They know which functional models. So nowadays the chips are ASIC chips are not only it has a single core, it will be multi-core processor, quad-core processor, or 8-core processor. Some server-based chip and all, they will have 24 post processors actually inside the ASIC chip, and across that there will be controllers, and there is a specific controllers. They will be interacting with the other devices basically. So they will decide which functional block has to come in which side of the chip, and everything they will function. Then there will be a design for test. The design for test. So let's get into the detail for each stage. This is the basic overview of the complete ASIC flow. So there is a so this timeline is also a matter. So if all the teams are working together, and they decide the fastest timeline for reaching this stage is a 1 year process minimum. But certain companies, they will release it every 3 months. They will release one tape out to achieve the market, to capture the market basically. To achieve this, so all the teams will work in parallel day and night actually to reach this. So one in each stage, if they fail, actually they have to rework everything all the way from the design specification all the way to the final tape out basically. So that's why, let's get into the chip specification. So this is a stage at which the engineer defines the features, microarchitectures, and functionalities, and where the time area, as I mentioned earlier, power, speed, what is the function or the ASIC has to go through. And here the major teams involved is design team and verification team, and also other teams also basically. So basically the chip specification once defined, RTL design team, they will tell, hey, these are the RTLs I'm going to do in this R0 release, and I am going to release it in this month actually. And after this month, I am going to release, after 2 months, I will release these features, and final release will happen this time. That's the plan they will do, and they will tell to the verification team. So verification team, what they will do, they will be deciding their major thing is they have to verify the complete all corner cases and make sure everything has to be tested on the chip. Even a single bug causes the multi-million-dollar. That chip itself is wasted. So you should not leave not even a single bug actually. So that kind of things actually they will do. So they will plan all the corner cases and everything, and based on the features, they will start doing all the test plans actually. So they will create a test plan document, and based on that, they will do all the verification strategies. So the second stage is the one where design team will start doing all the microarchitecture document. They will review with architecture architects basically. So the architects is the person who is able to know all the flows. Actually, they won't stick with the single flow. They know what is happening in clock tree structure, and they know what is happening in the final verification strategy, GDS2 flow, where the issue will come. So they anticipate issues because they might experience on different chip deliverables. So they anticipate delay issues, and they will plan all these things in their work plan. So they will instruct their teams, hey, this is what you guys need to take care actually. So they will review these microarchitecture document. Design team will review the microarchitecture document before going for a RTL development basically. And what their thing will do is they will, once the initial SOC development happens, and they will run a basic sanity test cases before releasing to the verification team. So the most of the time, the interaction with respect to the specification won't happen with verification team, because if verification team and design team they are discussing about the microarchitecture document, if any issues design team is done by the design team, verification team won't capture it, because both are discussing about the specification. That's why they won't discuss the specification between them, but instead they will discuss separately to the architect basically if they have any issues. So mostly once the specification is freezed, verification team expectation is they will receive the RTL database, and they start doing the verification actually. So they will have a separate microarchitecture document for their bus functional models, and also they will have a sanity, what are the test cases to verify each modes basically. You can see the flowchart here. So the first, the spec review with the design team, and what is the spec reviews? These are the UVM structure I'm having, and they will review their verification test benches with them, and what are the design specification acceptable and not acceptable. Everything is design specification is not acceptable, they will ask the design team, hey, this is the design specification which is not proper. They will please provide me the proper inputs. Like that, they will go and ask. Then the complete UVM test plans will be composed by the verification team, and again they will go for a test plan review with the design, and based on that they will go and develop all the test bench components, and they will run all the regression. Is the one major thing. Like if you run one single test, we call it as a single test case failure or something like that. And if you have thousands of test cases, you cannot run everything on a single one by one. So what they will do, they will create a complete script and they push it in a server actually. So what they will do, the server will backend, they will run all the test cases in multiple threads actually, and the results will be accumulated in a log file. So thousands of test cases will run and finally get updated in the regression log, and if any failures are there, it will indicate actually these are the test cases failing. And so the complete regression should pass for the complete features whatever they released by the design team. If there is a issue, then they will report to the design team to fix it actually, and that's how the complete verification strategy will work basically. So in verification, there are different levels of verification. Code coverages is there. So what they will do, all the scenarios in your RTL, there will be multiple lines of code. So all the lines has to get verified actually. So code coverage is nothing but all scenarios has to cover. If any scenario is not covered also, they will discuss with the, hey, why the code coverage is not coming 100%, they will discuss and they will close and make it 100% actually. Then RTL synthesis. So RTL synthesis is nothing but they will convert the complete HDL, means whatever RTL you are writing, that has to convert into netlist, get level netlist. And that is the flow. In this flow, actually, the DFT techniques also will get into picture actually. So the major thing is while planning the RTL synthesis, the constraints for the how much timing constraints, everything has to be placed, and also they will plan for DFT techniques. So DFT insertion they will do basically. So why we are having DFT? So DFT is designed for test, and this is a major very important in ASIC basically. And without DFT, it is very tough to test the chip once your chip has been come from the fab, means a test chip, what we call it as. So I forgot to tell you one thing. So you can see the final tape out, the stage here, and once you are getting the chip actually, so this DFT insertion where it works, where it is useful. So this you are inserting some DFT scenarios. DFT is you are designed for test actually. You are inserting, there are different type of DFT insertions. I'm not going to talk about much detail about it. What is the purpose of DFT? I will tell you. So purpose of the DFT is you are inserting in the design time frame itself. You know all the functionalities of the ASIC, and each functionality can be tested, and then only the mass production has to be happen. So for that, what is the shortcut method is they will insert all the DFT inside the design. And once the chip tape out happens, the first chip production will come. They won't be go for a mass production. There is a test chip will come into the picture. First test chip will come to the lab, and what they will do, they will run all the automated test cases with the DFT engines. And if any failures happen in the DFT flow, then definitely whether it is a potential failure, or then they will, whether it can be fixed in the software or it cannot be fixed in the hardware. If it is a hardware bug and they found it is a design bug, then what we call it as a ECO. So again, there will be a complete turnkey has to happen basically. Again, the whole step has to be followed for that particular feature. Again, they will do all the DFT checks. Once everything is passed, then only they go for a mass production of tape out actually. Yeah, so here comes the RTL synthesis, and there are different types of tools available in the market. Design compiler, and there are major EDA tool vendors are Synopsys and Cadence and Mentor Graphics. These three companies are the three major EDA vendors. EDA vendors is they are the masters in creating each stage actually. So each company has its own specific tool flow for a tool for verifying each stages of the ASIC basically. So for RTL synthesis, design compiler is a very famous tool for synthesizing the RTL. And other so Encounter is there, and HDL designer for Mentor Graphics. These are the tools. So next comes to the chip partitioning. Partitioning is a process of dividing the chip into small blocks, and this is done mainly to separate different functional blocks and also to make the placement and routing easier basically. So so again, this will be discussed again with the packaging designers, and it is not a single man decision. But again, if any issues are coming and how to partitioning the complete chip, they will plan it with accordingly the PNR team, because the place and route is one of the important factors and timing is one of the important factors. So if your critical path is more, then timing achieving is very tough. So they know where to position your block and where to keep the blocks to achieve the higher speed. So that's why the partitioning is the major step nowadays in the industry they followed actually. So you can see that to meet the capacity constraint, reduce interconnect demands, meet the performance requirement, the partitioning is very important in the ASIC actually. And DFT insertion, as I informed earlier, there are different types of DFT insertion techniques are there: scan path insertion, BIST insertion, and automatic test pattern generation. So basically, what the scan path insertion, there will be a small logic where we can test actually linking the register element into one long shift register. This can help to check small parts of the design instead of the whole design in one go basically. So only the small portion of the design you can test it with the scan path insertion. And MBIST is mainly for memory basically. So you will be in any ASIC design, if you have a memory component inside your ASIC, then this DFT MBIST will be DFT insertion they will do, and they will want to check all the memory. So they have to test the complete memory inferred is properly inferred or not, whether the memory completely inferred and it is has to write all the addressing till the end and wraparound should happen. Everything they will test it here in the DFT side. And automatic test pattern generation method is one more important thing. And there are devices already available in the market. There is a separate companies who develop the design for test technique. Testing components to test after that is called post silicon validation. So they will pump all the scenarios of the test cases inside the test chip, and they will test the complete chip. It will take some time, and means in 3 months time frame or 1 month time frame they will test it. And once the test everything passes, and if any issues they see, and they will come back and say, they will discuss, hey, this is the issue I'm saying, is it possible to fix it in software? If it is not fixed, it is a design issue. If the particular logic itself is not at all working, one of the important features that is for example, you are doing a chip, and the one particular feature is mainly targeted for this particular deliverables. If that particular feature itself is not working, and this is the issue they are finding in the DFT test cases, then what they will do, they will go for a ECO. Then ECO means they will retune the complete design, and again the complete flow will happen. Then again go for another test chip generation, and tape out will happen, and again they will go for a DFT check, and everything has to pass. Once the post silicon validation passes, then only they go for a mass production of the chip. Yeah, the floor planning, it's again once it is very important step actually. After DFT, the physical implementation process is to be followed. So in physical design, the first step is RTL to GDS2 flow. It is the process of placing a blocks in the chip. It includes block placement, design portion, pin placement, power optimization. So nowadays, the floor plan determines the size of the chip actually, and places the gates and connects them with wires, and basically the life of the IC depends on the proper floor planning basically. And if the life of the IC and also cost. So if you're floor planning, you just think about your home, and if you construct in your 2,400 square feet area, for example, if you are constructing a house for 2,400 square feet, if you are utilizing the whole area, definitely the cost will be high. And if you are planning for a 600 square feet, even though you have a 2,000, then the cost will be very less. Just similar way, what they will do, they will try to minimize the size and utilize all the features. In 600 square feet, you are able to keep left and everything, all the features in your all things, whatever you want to achieve in 600 square feet, whatever dream home you are planning, everything, all features will be there in your 600 square feet. Then you are the best. Correct? Similar way. So more features, reduce the size. So if you achieve it, then the cost will becomes low. So that's why the important planning is floor planning. and it is mainly for minimizing the total chip area, making the routing delay and faster basically, and improve the signal delays basically. And placement, and again, so placement is a process of placing the standard cells. So any chip tape out happens, they will target for particular nanometer technology. So the standard cells, they what we call it as standard cells. So now it is 7 nanometer technology. Currently it's in the market, and 5 nanometer technology is the one thing which Intel doing R&D. So these kind of things people are so that standard cells where to place, and so poor placement of placement requires large area and also degrade performance. So these floor planning, placement, and clock tree stages and routing stage, everything will be handled by a single backend team basically. So and also the major placement is also important is placement routing stage, where reducing the timing violations basically. So timing violations in the sense setup and hold time. So setup time is a major root cause for improving the design, and hold time is also data path delay. So there should not be any data path delay in the chip actually. If there is a hold time violation, definitely the chip has to be thrown out. You cannot expect the chip to work basically. So both setup time and hold time violation should be avoided in any chip actually. And clock tree synthesis, it's majorly for low power design, and the clock tree synthesis is the process of building the clock tree and meeting the defined timing area and the power requirements. So there are different clock trees available in the structure. It again depends on how you are designing the chip actually. It is not there is a specific design structure you should go. It again depends on how much power consumption and how much delay based on your functionality of your chip actually. So mesh structure is there, hedge structure is there. So inside these are the clock blocks actually. So your hedge structure, for example, this is a one island of a functional block where the clock will go in this structure basically. And if it is a fish structure, it will be like goes actually below. That is here. It is like a fishbone structure actually. You can see that actually. So clock is also matters basically. When you just think about it, you have n number of logic, and in n number of logic only you are passing a clock to all the logic at a time, and unnecessarily what will happen, all the logic getting toggled, but the functionality for that particular operation is only one block has to get operated, remaining other blocks has to keep optimized. Means there is no need of activating that particular logic. If you activate, so that is the intention basically, but unnecessarily the clock is passing to all the logics. For example, what is happening if your clock is passed to all the logics, power consumption means unnecessarily the logic gets toggled, so the power consumption get increased. Unnecessarily you are facing a power consumption. So to avoid this, they will go for a gated logic, and they form a proper clock structure, and to avoid unnecessary delays in the routing basically. So that is a major advantage nowadays to go for clock synthesis, and have a proper timing to achieve the timings basically. And routing, so place and route, basically the routing is again efficient routing is one of the major important process. So routing is a process of creating physical connection based on the logic connectivity, and signal pins are connected by routing metals interconnects. So there are different type of routings available in the market, like global routing, track assignments, detailed routing, search and pair. So these are basic algorithms, and what they will do, they go for certain algorithms in the, so the tool. So it's not like everything is manually they will take it. There are tools which will enable the backend operation of routing, and the efficient the tool will suggest first what this is the better routing, then manually we will place the proper logic and they will do a routing basically. Finally, the physical verification and timings. After routing, ASIC design, layout undergo the 3 steps of physical verification known as sign-off checks. Basically, layout LBS is a process checking the geometry, layout, and matches the schematic and netlist. And DRC check actually is a process checking the geometry in GDS file basically. And logic equivalence check is a process equivalence check between pre and post silicon layout. So in design in functional verification is itself there is a in RTL synthesis and between RTL synthesis and functional verification, what they will do there is a logical equivalence checking actually. What we call it as LEC. So what they will do, they will there is a tool LEC is there. So before that synthesis, they will do all the verification and also the pre and post design. All the layout has to compare, and they will check actually well what is intended logic functionality and what is the expected logic. So both has to work basically. So GDS2. So GDS2 and fabrication and packaging is the major means the process followed after GDS2. What they will do? The GDS2 is nothing but a graphical data stream interface interchange. Is a file produced and used by the semiconductor foundries. So most of the companies they won't have any fabrication foundries basically. Only few companies has their own foundries in the company wanted for, because it's a very costly process, and most of them are TSMC and basically it is located in Taiwan. So and this fabrication process actually, so what till GDS2 people do any service based company or product based companies, they do develop their chip, and they till GDS2 they will develop, and after that they will give it to the fabricators, external fab companies. They will give it to the fab company. Then fab company will take this GDS2 file and start doing all the packaging and this stuff. And that's how the things will work in the market, because if you have your own foundry, it is very costly to maintain actually. And again, the technology node has been go on changing every year. Now it is 5 nanometer technology. I don't know whether in future it can be 1 nanometer technology or beyond that. Who knows? So for that, actually, you have to have a fab which is very costly. So it will be a group of companies will be maintained. Sometimes the fab process, and even a chip will develop basically with a partnership. Basically, it's not a single company will develop a chip actually, because of the funding will happen between two companies. The joint venture also they will do that. Till JDS2 flow, a company will develop, and after that the chip wafers are will come, and they will split. This is out of this wafer, these many components we will split it to our company, and these are the components you can split it to your company 50-50 share or something like that. That also they will plan basically. So in this flow, they will do complete wafer processing and packaging and testing everywhere, and finally the tape out will happen. And after that, the ECO means post silicon validation. Post silicon validation. This is how the structure of post silicon validation. So what they will do, they will, once the chipset, you can see a chipset. A chip comes to from the, it is a just chip. What we call, we have all the DFT insertion. Everything is in the chip, and using the external thing, they have a separate environment they created for once a post silicon test chip comes, they will insert it in a board, and they have a they keep it ready actually. These are the things already parallelly they anticipate. Hey, after 3 months my chip will be there, because design team everybody already started. They also know what are the test cases has to develop and what kind of things they will keep it ready. Once the chip comes, immediately they will start the activity, and within 1 month time frame they will do all the basic testing and everything they will do, and in rigorous testing will happen basically. And if they found any issues, major issues, then definitely they will inform the team, and they have to retune this structure, means retune the design, and they will go for another tape out basically, fixing all the issues. And this is what pre-silicon, what is pre-silicon validation basically. So in each stage, I'm going to talk about only pre-silicon validation in detail now. And pre-silicon validation is the process to test and verify the ASIC chip before tape out, and at what stage we do, and we do majorly on once the full RTL, the stage-wise RTL, we are releasing to the design time. You can see that this is the stage we do pre-silicon validation. This is a common word in the industry. Pre-silicon validation means it can be an RTL simulation, it can be formal or static verification, or it can be an FPGA or emulation-based validation. So this is called a pre-silicon validation. What they do, there is a separate team involved. RTL simulation is nothing but a verification team. So what they will do test development, everything will be done. Static verification is again a part of a separate formality kind of tool, and they will do all the checks of the design, and they will do all the process. There is a separate design team is there for FPGA based simulation. So they have a separate environment for testing the complete SOC on the FPGA based environment, and they will run all the test cases. And then once all the test cases, which are all the test cases run by the verification team, they will also run and make sure all the test cases pass. Then they will say, hey, all the functionalities are working in the FPGA based environment, and they say they sign off actually. And parallelly, there is a emulation based validation environment. Emulation based environment is a okay. I'm going to talk about it. So emulation based environment, I will go directly here. So this is one of the emulation based. It's like a bureau kind of a machine where we call it as Palladium platform or Veloci platform, where they will put the complete multi-million gates inside this emulation platform, and they will run all the test cases and make sure all the test cases pass, and then only they will release it. So yeah, so this is the basics of pre-silicon validation. There are different varieties of pre-silicon validation they are doing in the market. One is RTL simulation, formal or static verification, and FPGA based validation they will also do, and also emulation based validation also they do. So all things can be done or parallelly will be used by the it is not that I'm doing ASIC tape out, and I'm already doing RTL simulation, and I'm already doing formality checkup. Why we need FPGA based simulation or emulation based simulation? Yeah, we'll think about it. Let's discuss further on that. So why we need a pre-silicon validation, and so basically that's a thing, right? So why we need pre-silicon validation? To make sure our multi-million gates has to work, and it has to verify all the test, all the functionality has to work in the and time to market actually is an important challenge. We need to do the functionality check, and all the timing scenarios has to met, and it has to be verified without any issues. So that is a major advantage of pre-silicon. Means that is the main important things of pre-silicon validation. So this typically requires modeling the complete system, where the model of the DUT may be the RTL. Another component of the system may be a behavioral or bus functional model. DUT in the sense, DUT is a design under test. So which is design under test? The ASIC chip which you are production going for a tape out. So it will be in the form of RTL netlist, or it can be an RTL, and it will be differs according to the platforms. It can be a netlist, and it can be a different form of netlist basically. And they will, if it is an FPGA, it can be a bit file. It can be if it is emulator, it can be in different form actually. But it will be a netlist basically. And file format only the different, but it will be in the form of netlist, or it can be a raw RTL actually for testing the pre-silicon validation. Main thing for the pre-silicon validation is you need to test all the functionalities. If you have 100 features, all the 100 features has to be tested. Unless you are not testing, and unless the sign off from the pre-silicon validation team, all the from RTL simulation team means verification team, they have to sign off all the test cases passed, all the code coverage is passed, then only they will go for tapeout. And from FPGA based simulation means validation team, they will go and check, hey, all the test case passed on this platform. Yes, it is passing. Everything is working. Then only they will go for a tapeout. And so all these things are parallelly they will work, and everything they have to sign off. Even one team is not going to sign off, they won't go for a tapeout, because the tapeout is ASIC chip is very costly and multi-million investment has been done on this chip actually. So all things in each stage, each function, each person involvement in the each stage of the ASIC tapeout is very important. So what are the different types of FPGA or emulation based pre-silicon validation? So one is emulator platform. Emulator platform, it can be Palladium platform. The machine is the Palladium platform is given by Cadence design system, and Veloci is one of the similar kind of platform, and it has its own capability. And this platform has been developed and given by the Mentor Graphics, Veloci. And there are another kind of platform by the industry using for the pre-silicon validation is custom FPGA platform. How it looks like: a single board, custom FPGA platform. In single board, there will be multiple FPGAs, and each FPGA has a communication lines will be there, and so the complete SoC will be partitioned and putting into the each FPGA, and they will do all the test cases running on this FPGA based platform. And next is the apps. There is a custom, apart from custom FPGA, the custom FPGA is what actually? Custom FPGA platform is in-house, a company. For example, I am working in Western Digital means, and in my company, the company itself spend their own board expenditure on developing these boards and connections, and whatever development is called custom FPGA platform. And there is a FPGA platform sold by the Synopsys and Cadence companies. They are called HAPS, ZeBu, and Protium. So these are the FPGA based platform to validate the multi-million SOCs, basically gate SOCs. So they will put all the complete SOC into this platform, and they will run all the test cases, and they make sure everything runs on the platform. Okay, so main advantage of these platforms. What is the main advantage? Why we go for a FPGA based or emulator based or custom FPGA based? Why can't we do RTL simulations? Think about it. Let's discuss further on that. So how the emulator looks like? Emulation is the use of specialist computer. So which this is an emulator, and I'm having it. So for example, this emulator is not necessarily needs to be inside next to me. It can be sits in US, or it can be in any other portion. So it will be connected in different ways actually. So you have a HDC cable. There will be a hardware connected to this. For example, there is a target board here. They connected this cable here, and I'm sitting in one machine, and remotely I'm able to access this machine, and I put all the netlist inside this Palladium platform. And what I'm going to do is I'm going to run here. For example, this is a memory sits inside this target board, and I want to do a communication from my SoC to this target board. What I'll do, I'll initiate a test case, and I'll do all the way. I'll write and read back all the transactions by sitting in my home, and I will do all the transactions. The machine will be sitting somewhere actually. So that is the major advantage of the emulator. And not only emulator, nowadays FPGA based platform and our custom FPGA based platform all communicated through Ethernet based setup. And it's not necessarily you need to go to the lab and you need to sit next to the machine, you need to debug it. No, only for certain very minimal IP development and minimal testing needs, then you can go and do that. Everything is automized, and everything it's a one-time connectivity thing. And if any issues you are stuck actually, for example a cable loose, There will be some persons, it's a lab maintenance person, daily go to the lab and they will do all the connectivity check, and they will make sure if any issues, then they will report to the people and they will check for the connectivities basically. That's how I'm just giving a big picture how the industries are using the emulators and all these things for pre-silicon validation. Okay, so as I told you, right? So we do between uh, emulation platform and FPGA platform. What is the difference, and how it is going through that? Before going to that, actually, before I am going to explain about this, I want to ask you the question. We do verification. I told you, right. We do RTL verification through UM test bench or Verilog test bench or whatever it may. I have a test bench environment where I am running all the test cases. And why we need a separate machine or separate team people sitting on the emulation? They are saying something emulation. You are saying, sir. You are saying FPGA platform. You are saying, and why people are spending a lot of money on it, and why separate team is sitting and working on it. So, for example, I just give you an example. You have a mobile phone, and a mobile phone has a complete processor in it, and it has a display in it. Everything is running. But if you don't have Android OS in it, will that mobile useful for you? No, right? So it's basically you need a software which runs on this hardware platform, and the hardware has to make sure everything it has a combined, right. If you are developing an hardware, and the hardware is I'm ready with the hardware, but if you are not having a software, then what is the use of that product actually? You need to have both hardware and software has to run both parallelly, and the development also has to happen, then only that product will be useful, right. So that's a major thing. You can do it through FPGA based platform or emulation based platform. What they will do, software team is a major important team. Apart from the hardware development, software means a firmware or software team also wants to test the they will also develop the test cases, putting the operating system on this platform, because you are putting quad core 24 core. I'm having a hardware, but without software, what is the use? And also time to market, right? My hardware is ready within 3 months, but your software is not ready. Again, I will sit after chip comes, and I will develop it software, and I will put my all the software on it. I will take another 6 months to deliver it. That by the time somebody in the market will release the chip with the software, right? Then there is no use at all. So both hand in hand has to happen. I'm starting a chip, and in another 3 months, ASIC chip is going to come, and parallelly it will work on the software. Also needs to work on that platform. What they will do, software team is also wants to be experiment, and what is the reset sequence happen once power happens. What is the bias has to happen? What are the controllers to come out, and how the display has to come while power up? Whether it is a Realme phone or it is a thing, everything is displayed on that. Everything will be taken by the software. So while you booting your phone, some display is coming, right? Everything is taken by the software. So these softwares are very important, and their development is also important basically. So they're hand in hand. So how they will do it actually? In RTL simulation, they cannot do it because everything they are coding and everything. They have a very limited features can be tested. Even if you want to run any test case on the RTL simulation, it will take a week or sometimes 4 weeks of time to run a test case and complete it, because you are running a complex designs. Nowadays all the designs are very complex, and all the scenarios will be covered, configure. So it will take to get a result in RTL simulation environment. It will be very tough to get the output in a day, because it will take 1 week time. So you have to wait for that much time to get the results. For debugging that result again, it will be a very time taking. So that's why they come up with a parallel way of doing it is emulation platform and FPGA based platform. What they will do, they will put all these things inside FPGA or emulation based environment, and what they will do, they do all the test cases, C code, everything, dump it in the FPGA based platform. Then the fast, because it's a hardware, right? Then your simulations and your test case runs, everything will be faster. And it will be, instead of, you don't need to wait for 1 week or 2 weeks, you just need to wait for 5 to 10 minutes, your output will come and immediately you will be able to test it, your functionality. And firmware teams also able to develop their code. If any issues are there, they'll fix it, all the things. So they know the power consumption also, because they will activate based on what is the functionality. Based on that, they will choose which block has to come first and which controller has to come later. All this design, it's a bootkit table, what we call. So everything they will decide, and they will do all the planning will be done in the FPGA based or emulation based platforms basically. And even any issues on the RTL, while running on the, because you are running a real software on it, and it will imitate everything as like a ASIC chip actually in the emulation or FPGA based platform. And while running the test case, you are seeing an issue, and it will be easy to debug it actually, and fixing it. And it is better to fix it on the order based platform, right? So it will be gives a more confidence to the before tape out basically. So this what, so increasing the gate count of SOC, the typical SOCs nowadays contains approximately 50 million gates. Simulators are practically not that efficient. Simulator in the sense RTL simulations. So performance to handle such a big designs are challenging. That's why they go for a emulation or FPGA based design. And majorly the emulation or FPGA based platform, what they want to do is they want to support BIOS and firmware team development tested, and before tape out, this cannot be, before tape out they want to test it. This cannot be achieved in a normal verification environment. And major thing is all corner cases, negative scenario cases. If you want to evaluate in verification environment, it takes months and times. And but but in a FPGA based emulation platform, it is very faster, and it can get the results in 5 to 10 minutes. So complete boot up sequence and reset release sequence. If your processor wants to, that's what the planning, right? So how to boot the sequence? If you boot up means the complete ASIC has to boot up. So while boot up, what are the things, controllers, which controller has to happen, which out of quad core processor we are having, right, inside the mobile platform or whatever it may be, and which processor has to start first, and which will come first and which will come later. So all this planning will be done in the FPGA based and emulation based platform. And the reset release, if you are even the processor boot up also, there is a reset sequence. These are the sequence has to follow as per the processor thing. Whether it is Intel processor, it is a Qualcomm processor, whether it is a ARM based processor, everything has its own reset sequence. You have to follow the reset sequence and release the signals properly. Then only the processor boot up will happen basically. So all these things are verified properly in the FPGA and emulation platform. That is a major important of pre-silicon validation about not only the RTL simulation, and these emulation and FPGA based platforms are very important actually. And bulk test cases with more than time intensive test cases can run on the FPGA version with lesser time. Okay, so let's get into the back side of, and okay, now you guys know about we are discussing about RTL simulation, and we are talking about FPGA and emulation based platforms. But between emulation and FPGA based platform, what's the difference? And why people are preferring emulation platform and also FPGA based platform? That is also important factor, right? Because we know we do RTL verification, and we also need to do emulation platform. We also need the FPGA based platform. Why these many platforms to before tap out? You can have a question, right? Am I right? So consider this is an SOC basically. So This is an SoC. SoC means what? System on chip. Why it is system on chip? A processor in it. If it is there is no processor inside a SoC, then we won't call it as SoC. It is just a chip. Okay. So system on chip. Why we are calling? Because a processor in it. So we are having a system on chip is called a processor in it. So just taking an example, there is an ARM processor and there is the interaction. There is the controllers are there. Ethernet, USB, UART, SPI, two-wire interface, so CAN protocol, so CAN controllers. So this is developed for some application, and I want to validate this complete SoC on the platform. Okay, so if I go for a Palladium platform or FPGA platform, how do I do that? So there are differences in it actually. So Palladium platform or the emulator platform, if it is a Palladium or Veloci, it is an emulator. Okay. So emulator platform has its own advantages. Inside emulator, what it is there, it is a processor based platform basically. And this processor based platform, it's a proprietary one. They won't actually reveal it because they are selling the box. Okay. And FPGA based platform, and it can be a custom based FPGA platform or it is a HAPS based FPGA platform. It is FPGA in it. Okay, so in this, what is the difference? How do I target these complete SoC inside these different platforms? What I'm going to do is I'm going to put this complete thing SoC multi-million gates into the Palladium platform in one single shot. That is a major advantage of Palladium platform. And there is no need of hierarchical. So I'm top file. This is my top file, and after this, inside this is the modules I have, and this is the hierarchy I'm following. So signal naming convention, everything will be same. There is no need of partitioning or no need of hierarchical change needs to be done, and which is very much useful for the designers when they face any firmware test cases issues are running in the Palladium platform. So I can put the complete SoC inside the Palladium platform without doing any change. And for the designer, it will be very easy to debug because if any test case fails, hey, I know which signal it's failing and I will probe that particular signal and I can see, hey, this is the signal I'm facing the issue, I will fix it actually. So the complete signal naming convention also will be preserved in the Palladium based platform. But what is the disadvantage of Palladium platform or emulator based platform? If that is the case, why we are choosing FPGA platform? Because Palladium or emulator based platform, they run it only at maximum speed of 1 to 2 megahertz. 1 to 2 megahertz, not more than that. So because that is a advantage, that is the only disadvantage we are having, but we can keep everything inside the Palladium platform without changing the hierarchy, and we can run all the firmware test cases over it. But again, compared to RTL simulation, 1 megahertz or 2 megahertz is much better. But FPGA based platform, maximum speed we can run it at 30 to 40 megahertz. But if each FPGA can capable to run at 600 megahertz to 500 megahertz, that's not an issue. Once you are putting the complete SoC into FPGA platform, how you maximum you can run it at 30 to 40 megahertz. Why? You can ask. Okay, so what is the issue? So there are you can consider the left hand side. There is an FPGA based platform. So in FPGA based platform, you cannot keep everything the complete multi-million gate inside the FPGA. I'm taking more time. So this FPGA based platform hello.
Sir?
Yeah, you guys are able to see that, right? Okay. So sure. Sure. So the FPGA based platform major problem is you have to partition the complete SoC and putting into the each FPGA is the challenge. You can, because each FPGA has a capacity of very less utilization. You cannot keep more than stipulated amount of logic inside a single FPGA. that's a major disadvantage, right? So that's why we have a multiple FPGAs, and we have so each FPGA has an interconnect. So between the complete SoC cannot be put it. So what I will do, I will put one processor in FPGA 1 and memory controller in FPGA 2 and other logics in another FPGA, and the interconnects will be happening between these FPGAs basically. So my that's the biggest time taking and time intensive task, but the speed can be much higher compared to the other platforms. So that is a major advantage if you go for FPGA based platform, and even the firmware test cases can be run very faster and able to achieve it actually. So that's it from. So that is the differences I'm giving. So this is the so basically between RTL simulations, and this is the basic advantage. So ASIC simulations are running with 900 hours for 400 random read write commands, but Palladium based simulation 90,000 random read write commands with 9 hours only. So just see the differences. This is the real time values which we got it actually, and this is a comparison chart between all the simulators, RTL simulation, FPGA based simulation, and emulators. So if you look into the vertical side, actually uh, this is a performance. So and so here you can see the green is RTL simulator, and blue is the FPGA prototyping, and red is the emulators basically. So blue color, you can see the performance wise which is higher, FPGA is higher, and next is the very lesser. So 1 megahertz is the maximum capacity for modern emulators, and simulations only lesser, very less frequency only can be run. And with respect to the left side design capacity, the emulators are high best, because you can put any million gates of in a single machine, single box, and you can achieve it. But if you look into the FPGA based thing means, then it will be like only lesser. So next to that, so and in green color, you can see that this is an RTL based simulation. So again, it is very less design capacity. You cannot run much actually. And if you look into the debug capacity, you can see it is in debugging on verification platform is very easy compared to other platforms. If you look into the development time frame, uh, RTL developments time frame. I'm not talking. I'm talking about the development time frame for the verification platform or these validation platforms. So RTL simulation environment can be done in hours, but this red color, you can see that modern emulators can be done in days. But if you take a FPGA based platform, it will take long time, because you have to properly partition. It has to functionally work, because number of IOs also reduced, and you need to do serializing the complete RTL from one FPGA to other FPGA. So serialization has to be done, and make sure everything works on the proper frequency. The whole SoC should be work on multiple FPGAs, and make sure it works on a single reference clock actually, right? The power up and everything will happen. So everything, the functional wise, it has to take. So it will take long time, and but it is worthful for to achieve the performance. So the firmware teams will prefer mostly to debug on, and development will happen on FPGA based platform. But RTL team develop fixing the issues, everything will happen on emulator based platform, and also the verification based platforms. So I think that's it from my side. Thank you guys. Any questions?
Dear participants, you can post your question in the question and answer section. Can you share your question, please?
Sure. Yeah, somebody has to tell me the difference between ASIC, SOC, and FPGA. So basically, that's a basic difference, right? SOC is a system on chip, and again, it is an you can make an SOC on FPGA platform and also in ASIC. But FPGA is just a configurable logic, so it is a SRAM based. But you can configure your FPGA to a SOC also. So that is the capability of SOC. But what is the advantage of ASIC? ASIC is a predefined. You need to define a logic and it's going to be an ASIC. So that is what ASIC, application specific integrated circuit, means only the uh, uh, you need, what is the application you are going to develop. That is the only thing you will target for ASIC, and it is specific to a particular application. You cannot do any configuration on that. First thing, and for example, where the ASICs are used, and you can ask. So most of the, think about LED TV. You can open a LED TV. You can insert, there is a motherboard. You can see there is a processor in it, and you can see multiple chips, right? So those are all the ASIC chips. Actually, it is defined for this particular application. For LED, it has to go through the display controller. Means then display will be there. Display controller, one particular chip will be there. So like that actually, but FPGA has different application. You can configure the chip for even LED TV application also, but it requires extra controllers. You have to develop a specific custom board FPGA, and you need to do all the specific interfaces. Then only you can do the even LED. I'm just giving an example. LED based display, LED TV based controllers actually.
Which land? So which language should remain either vanilla or VSTL? Or system?
Which language?
Which language VLSI engineers should familiar either Verilog, VSTL or system Verilog? Which language?
Okay. Sure. So basically, VLSI engineers, it's not about the language. Basically, they has to be very strong in digital first. So in the market currently, Verilog and System Verilog are the major because in US-based companies are using System Verilogs and Verilog. But if we are going for a German, UK-based companies, they all conventionally using VHDL. So it is again depends on the company-wise, and moreover, it is not about language. You should be very strong in the digital concepts. If you are strong in digital concept, there is no barrier in developing a logic to code it actually. If you are strong in digital, any logic can be converted into hardware description language. So language is just a syntax where you can convert your thoughts of digital logic to the hardware description language. So it can be any language. You can, if your person knows Verilog or System Verilog or VHDL is, I am comfortable with system VHDL. There is no harm in saying that I know only VHDL. A company, so they won't. Any companies don't say, "Hey, you know only VHDL. I cannot prefer you." It's not about that. If you are strong in VHDL, you need to be strong in digital. And if you are strong in digital, you can able to convert anything to your language, because whatever language you are free, just it's a syntax, right? So you can convert anything very faster. Am I?
One more question. Difference between emulator and simulator.
Yeah, so emulator, that's what I told, right? So simulator is nothing but an RTL simulation. Basically, you are developing a UVM based verification environment, and where you are running on a server. Server is nothing but it can be a Linux based server, or it can be a Windows based server, or whatever maybe. So it is just a you are already predefined processor. You are having a Windows machine, you are running a simulation. That is called a normal RTL simulation, right? You are opening a small tool called what you call model sim or whatever. It's a normal RTL simulation. I'm just giving an example. So if you are going for emulators are what? Emulators are a big machine where multi-million words have been put it into that machine, and a few more test cases and all the test cases can be run on that machine. There is a complete setup. There is a complete team is working on it, and they will take care of the complete emulation platform. So the emulators have been built with respect to, it is like a big room size machines. Actually, I can say that. That's why I also shown in the picture, right? So you can see this left-hand side picture. This is an emulator. You can see how this is inside the lab. So you can see that how big it is. So there are different connectivity of Ethernet, and multiple people can work on these emulators. It's not single person can work at a time. There are 8 to 10 people can work at a time on these emulators basically. So though they will have a particular domain level partitioning, and after that multi-million gates have been put into these emulators, and parallelly 8 to 10 people can work on this same RTL code, and they will run their own different tasks. I'm the responsible for display controller, means I will run all the display controller test cases and I will test it on that. Somebody will have a ownership of processor power up and all these things, then they will run all the processor power up test cases on the emulator and they will test it. So like this, they will split all the things and they will make sure everything runs on the emulator platform. And again, don't run anything on any RTL simulation test. Similar functionality, but the way they run it is everything by processor. So everything will dumped on the based test cases. So how SRAM is, they will simply run all the hexadecimal values and they will run it in, fuse it in the RAM fuse, and the processor will read those RAM values, and the power up will happen, then configure those registers, then the test case you can run actually in the C code basically. That's how the emulator works.
Okay, thank you, sir. Any fabrication centers in India? IC fabrication. Any IC fabrication centers in India?
No, sir. Actually, no. In India, it is not there. Only Taiwan and China, they have the fabrication centers.
Okay, sir.
There is no fab in India.
Okay, sir. So, our question is, FIR filter for delays and deep flip-flop is used. Instead, is it possible to use asynchronous deep flip-flop?
I'm sorry.
In FIR filter, for delay synchronous deep flip-flop is used. Instead, is it possible to use asynchronous deep flip-flop?
And again, it's again.
They are asking whether we can use asynchronous deep flip-flop for FIR.
I think the FIR, you are asking about some FIR filter logic.
They are asking like that only.
In FIR filters, you are asking, can we use asynchronous flip-flops?
Yes. That is the question.
Yeah. Okay, so so basically what you are trying to do here actually in FIR filter. So you are developing a filter and it's it for if it is for FPGA and you want to test it actually. If it is a simulation based FIR filter or that's what actually. So if it is an ASIC based FPGA filter, again the design will differs. You have to target as per the technology library what you are targeting. Again, you can use asynchronous filters and asynchronous D flip flop. Asynchronous D flip flop in the sense you are talking about asynchronous resets.
Yes, sir. Yes.
Yes, again, so there are multiple cases actually. So if you are using an asynchronous reset, you need to take care of reset release also. So you should have a proper release logic actually to take care of the asynchronous release logic, because you are setting a reset with respect to irrespective of clock, but to release the reset based on the clock. So there are logics to be developed to achieve the asynchronous reset, and synchronous release has to happen basically, or else you will face a setup and hold violations. So you need to take care of it properly.
Okay, sir. Thank you, sir. I think that's all about question.
Oh, great.
Thank you for a wonderful session, sir.
Thanks, guys. Thanks, everyone. And I'm pretty sure you guys enjoyed the session. And moreover, in this pandemic situation, everybody stay home. And thanks for joining this session. And I think everybody, all the best to every student, each and every students, and stay safe. Thank you.
Thank you very much. Dinagaran sir, you can join. Yeah. Mute mute. You are in mute, sir?
Yes, sir. So, good evening to all. It is our great pleasure to see you in the 5-day, 1-week faculty development program. And I hope all the participants might have got some very good knowledge enhancement by this 5 days course. Actually, so it is tough to accumulate this much eminent professors and industrialists in a single umbrella to share their knowledge. But the Department of ECE has done a very good job. They have taken tremendous effort to bring all the expert members in a single umbrella in the name of 1-week faculty development program. I hope this will be a very good knowledge sharing, and I hope all the participants will be able to go for a good classroom teaching, and as well as this will help them to enter in a very good research area as far as electronics and communication is concerned. And I hope, so while we were discussing about this FTP, we have repeatedly told that this will not only be useful for the electronics and communication faculties or students, this will also be useful to all the circuit branches faculties and students to enhance their capabilities in the research as well as to enhance their fundamentals. I hope the right job has been done by all the expert members. And on behalf of Chennai Technology, it is our great pleasure to once again for your all supports, and thank you so much. Thank you so much, all the coordinators, and especially Tanagopal sir, to conduct a very good program under the umbrella of Knowledge 4.0. And this webinar series is being successful, and we are able to conduct in different scenarios due to the motivation what we are constantly getting from the management, especially from our honorable chairman. So at this point of time, so I would like to also express my sincere thankfulness to our management and our honorable chairman sir. And thank you, Tanagopal sir, for your wonderful organization. And I hope so many efforts have been taken from all the faculties of ECE. And also, thank you so much. And thank you so much, participants, for being with us and for your support. Thank you, sir.
Thank you, sir. Thank you, Dr. Thank you very much, all participants. Hope all experts are satisfied with requirements. So thank you very much for your participation. We will share the feedback link today evening, and also certificate within tomorrow. Certificates will be issued. Thank you very much. They are planning to organize a conference in the month of September. So I would like to hope you all join us again. Thank you very much.